In this video, we are going to introduce covalent bonds. So we're going to talk about covalent bonding, how the bonds form, and how we represent them, and a little bit about the energy of covalent bonds. So we've seen ionic bonding, which is the giving and taking of electrons by atoms to form charged particles, ions, which are then held together by electrostatic interactions. And we saw that in, for example, the solid state, ionic compounds don't exist really as molecules. They exist as a bulk with lots of ions, but they're not really connected to, one ion isn't connected to any one specific other ion. They're just surrounded by ions of opposite charge. And this is not the case for covalent bonds. So covalent bonds occur when there is a sharing of electrons. And this happens basically as atoms approach each other, depending on the types of atoms here, but especially in the case of, say, two nonmetals, in this case, two hydrogen atoms. When they approach each other, the first thing that happens is their valence electrons repel each other a little bit. And then as they get closer and closer to each other, what happens is that the electrons from one atom start to be attracted to the nucleus, of the other atom. And eventually that attraction balances so that we reach a potential energy minimum, the lowest energy arrangement of these atoms. And that is what we call a covalent bond. If they get any closer, then the nuclei start to repel each other, and you can see the potential energy goes up to infinity. Now, the formation of covalent bonds is spontaneous if the overall process results in a system with lower potential energy, and forming covalent bonds is always an exothermic process. It always gives off energy. Breaking covalent bonds requires energy. Now, we saw in our discussion initially of bonding that we talked about how we represent atoms and their valence electrons, right? Using Lewis dot diagrams. And so, for example, we could have hydrogen with its one valence electron like that, or chlorine with its 7 valence electrons, maybe like that, right? Now, the key thing here is that unpaired electrons in atoms are the ones that are going to participate generally in covalent bonding. In nature, unpaired electrons are often referred to as free radicals. They are unstable. Molecules are in lower energy states when electrons are paired, for the most part. And so what happens is atoms can share electrons so that they have all their electrons paired. And you can imagine basically that the atomic orbitals that these electrons are in, so s orbitals or p orbitals, they're going to overlap with each other so that we get a covalent bond. So for example, between a hydrogen and a chlorine, each of these atoms has one unpaired electron. And so I can write this like this. Now, if I bring these together, I could write this, for example, like this. Now, this here represents a covalent bond, which has 2 electrons. And this is fine for the most part, but this kind of notation gets messy when we start dealing with atoms or molecules that have multiple atoms and lots of bonds. And so typically what we actually do is, instead of drawing those two together, what we'll do is we will represent them as a straight line. Like this. Now, the formalism that we're going to use for drawing right now is something called Lewis diagrams. And there are some rules when it comes to Lewis diagrams. And some of the most important ones are you have to show all of the valence electrons, ones that are in bonds and ones that are also non-bonding electrons. So these ones here, right, these are all non-bonding electrons. They are not participating in the bond. So this here, again, this is now our covalent bond. And it has 2 electrons. These electrons here are what we call non-bonding. Right? They are not participating in bonds. So that is really ultimately what it comes down to. Now, there are a bunch of rules that we're going to talk about in terms of drawing what we would call valid Lewis structures, or Lewis structures that are going to represent the molecules as close as we can approximate them. Here, what I've drawn is a single bond. There are double and triple bonds in covalent molecules when atoms will share multiple pairs of electrons. So we could take an example of, say, carbon dioxide. Now, it's going to be very useful for you to start remembering the common bonding patterns of the different elements, especially those in the second row: nitrogen, oxygen, carbon, the halogens, because it makes the process of drawing Lewis diagrams a lot easier. So, for example, hydrogen pretty much always forms one bond. The same is true for the halogens. For the most part, they also only form one bond, except in a very few restricted circumstances. Carbon forms 4 bonds, nitrogen 3, and oxygen 2 in general. Now, if we think about the molecule carbon dioxide, so the way I would go about figuring out the Lewis diagram for this is to draw Lewis dot diagrams for each of the atoms that I'm dealing with. So I have carbon, I have an oxygen, I have a carbon, and then I have another oxygen. Now, as a rule, the atom that can make the most bonds is going to be what we call the central atom, the atom that's in the middle. And there are a number of different ways that we can connect, for example, a carbon to 2 oxygens. I can think of a few different ones. And now you probably have all seen the structure of carbon dioxide, but that doesn't mean we can't think about how this happens. For example, I could imagine, say, pairing these two, right? This guy, and then this guy and this guy, and then these two here, for example. So that would give me something that looks like, say, this. Now, a structure like this is problematic for a lot of reasons, and it brings up a bunch of the stuff that we actually need to talk about. So, the first thing is that in small molecules, small covalent molecules, rings like this, or cycles, are allowed, but as we will see a little later on, geometry kind of matters here. And this kind of system is very strange. Rings with 3 atoms in them exist, but they're not very stable. Now, there's another bigger problem, and that has to do with what we call the octet rule and formal charge. Now, the octet rule says that, for the most part, atoms in molecules want to have a full octet. They want to have 8 valence electrons. And you can think of this as having basically a full s and p valence orbital, right? So, for example, oxygen and carbon are both in n equals 2, so they want their 2s and 2p to be full when they're bonding. This gives us the lowest energy arrangement. So that's the first thing, is the octet rule. And the other thing we need to watch out for is something called formal charge. So we need to make sure that the charges are balanced. Carbon dioxide is a neutral molecule, so we need to make sure that if there are charges in this molecule, that they all balance out to also equal 0. Now we're going to look at drawing ions a little bit later on too. So let's take a look at this version of carbon dioxide and see how it holds up. So there's two different ways to count for the octet rule and for formal charge. So let's look at both of those now. All right. So the first one we're going to look at is the octet rule. So the way we count for the octet rule is we're aiming for 8 valence electrons. And basically what we're going to do is we're going to count all of the electrons. So we count all of the bonding and non-bonding electrons. All right. So, and we want them to add up to 8. Now, we're going to see cases where there are exceptions, either more or less, but we'll deal with those a little later on. Right now, we're going to focus on molecules that respect the octet rule. So let's look at, say, this oxygen atom here. So if I count, first I'll start with the non-bonding electrons, 1, 2, 3, 4. That's great. Now, the thing is in covalent bonding, when we're looking at the octet rule, because electrons are shared, we actually can double count, right? This covalent bond has 2 electrons in it, and so does this one. So 1, 2, 3, 4, 5, 6, 7, 8. So this oxygen here, this oxygen respects the octet rule, right? It's okay. 1, 2, 3, 4, 5, 6, 7, 8. This one is also okay. Let's look at this carbon atom now. 1, 2, 3, 4, 5, 6. Uh-oh. So this one only has 6 electrons in octet. So it's not even really an octet. So that's no good. That is a higher energy situation. It's not ideal. So that's the first thing, this arrangement. And that right away is you would stop. All right. And we're going to learn where we're allowed exceptions to the octet rule. Carbon is not one of them. So right away, if you draw a structure like this and you check, you count for your octet rule, right away you know, oh, carbon is missing electrons. This is not a good structure. Now, we're going to use, even though we already know this isn't a good example, we're going to use this for counting formal charge as well because it illustrates the point. So in the case of formal charge, we count all the non-bonding electrons. And 1 electron from each bond. But there's an additional step after we count. What we have to do is then we have to compare that to the neutral atom. So what does that mean for us? Well, let's look at this oxygen atom here. So if we're counting for formal charge, we say this has 1, 2, 3, 4, 5, 6. So for formal charge, this has 6 electrons. Now, when we look at oxygen on the periodic table, its valence is 2s2, 2p4. So neutral oxygen has 6 electrons. So the difference between 6 and 6 is, well, 0. So this oxygen atom has a formal charge of 0. What about this oxygen atom? 1, 2, 3, 4, and then 1 electron from this bond, so 5, and 1 electron from this bond. So that's 6. And again, we say in this molecule, that oxygen atom has 6 electrons around it for this accounting method, for this counting this way. And a neutral oxygen atom also has 6 electrons, so it also has a formal charge of 0. Now, remember, carbon dioxide is a neutral molecule, so the sum of the charges in the molecule has to be 0 in this case. Now we're going to count for carbon. 1, 2, 3, 4. Now, carbon also has a formal charge of 0, of 0 in this molecule because carbon is 2s2, 2p2, so it also only has a formal charge of 0 here. So in this case, the formal charges work, but the octet rule is not obeyed. So when we are evaluating this structure, those are the two things we have to look, is we have to check. So octet rule, yes or no, and then formal charge. So we saw for this molecule, formal charge, yep, it's good. But octet rule, bad, right? It doesn't, the carbon has an incomplete octet, so then we can say this is not a valid structure. So now if we're going to try and come up with a Lewis diagram for carbon dioxide, we need to try something else. So let's go back to our atoms. We've got carbon, and then we've got oxygen, so again, we're going to start by just connecting the carbon with each oxygen one time. So that gives us something that is going to look like that. And we can see that there are still unpaired electrons, but we can just pair them up like that to give us a Lewis diagram that looks like this. Now, I've drawn it linear in this way with everything in a straight line. It's important to realize that Lewis diagrams don't have geometry. So I could have drawn it, I did draw it like this. I could have drawn it just as equally like this. We are going to explore the actual shapes of molecules and drawing in 3 dimensions. And when we do that, then guess what? The way you line all your atoms up matters a lot. But actually, for Lewis diagrams, it doesn't matter at all. So let's take a look at this version of carbon dioxide and see if it meets our criteria. So the first thing we're going to check is the octet rule. So let's look at this oxygen atom. 1, 2, 3, 4, 5, 6, 7, 8, right? So each of the non-bonding electrons and both electrons in the bond. So this oxygen respects the octet rule. What about the carbon? 1, 2 from this bond, 2 from this bond, so that's 4. 2 more from this bond is 6. 2 more from this bond is 8. So this one also respects the octet rule. And then this oxygen, well, it's the same as this one in terms of how it's bonded, but let's take a look. 1, 2, 3, 4, 5, 6, 2 more from this bond, and then 2 here, 7, 8. So this one also respects the octet rule. So we're already ahead of the game. But let's check now formal charge. Right, so put that in orange. So remember, For formal charge, we count a little bit differently. We're going to count all of the non-bonding electrons and one from each bond. So 1, 2, 3, 4, 5, 6. So we're 6 electrons, and 6 minus 6 is 0. So good. 1, 2, 3, 4 for this carbon, and carbon neutrally has 4, a carbon atom, so 4 minus 4 is also 0. And 1, 2, 3, 4, 5, 6. Again, for oxygen, 6 minus 6 is 0. So formal charge works. So this is a valid Lewis diagram for carbon dioxide. Now we're going to see as we move forward that as molecules get bigger, they have more atoms, that in fact you can often end up with multiple valid Lewis diagrams. And that's a whole other bit that we are going to be looking at. Now, before we move on, what I want to spend a bit of time talking about is the strength of covalent bonds. And there's a parallel to be drawn here between covalent bonds and ionic bonds. If you think about covalent bonds, ionic bonds rather, if you think about ionic bonds, how did we judge their strength? So for ionic bonds, we used our old friend Coulomb's law. So what does that mean? And we said, well, there's the product of the charges and the internuclear distance when we were evaluating lattice energy, which is the strength of ionic bonds. Now, so we have charge and ionic radius. Now, for covalent bonds, it's a little bit different because there is no charge, right? The atoms aren't charged for the most part, and these aren't ionic compounds. So we have to evaluate things a little bit different, but there are similar things. So instead of ionic radius, actually atomic radius is the thing we're going to look at. And instead of the charge, though, we're going to look at what's called the bond order. So how many bonds are there between two atoms? So let's start with atomic radius. So if we look at bond length first, what we're going to notice here is that the bond length ties very nicely to atomic radius, right? The covalent bond length is really measured as the distance between the nuclei involved in the bond, but we can estimate that, or at least in terms of ranking, by looking at the size of the atoms. So for example, we see that I2 has a longer bond than, say, Cl2. And we can also make the same inference then that the I2 bond is going to be weaker than the Cl2 bond. Now, the other factor that I mentioned was bond order. Now, bond order really just means what kind of bond is in the molecule. So are we talking about a single bond, a double bond, or a triple bond? So if you look up here, what we see is that first of all, the bond order ties into with the bond length also. So a single bond has a bond order of 1, and we can see for carbon-carbon single bond, it is the longest of the 3 bonds here, right? And that it is also the weakest of the 3. The carbon-carbon triple bond is the shortest and strongest. So those are the 2 factors that we are going to be looking at in terms of dealing with the strength of covalent bonds. Now, when we were trying to look at things like lattice energy, we used a complicated system, the Born-Haber cycle, to use all these other quantities to figure out what's going on in terms of the strength of the bonds. We used a Born-Haber cycle to try and get at the strength of the lattice energy. Now, for covalent bonds, it's a little bit easier. And we're going to look at the process in detail a little bit later on. But to give you a sense of what actually is happening, what we have to do ultimately here is look at the bonds that are broken and the bonds that are formed. And the difference between them, between the energies of those bonds, is going to be the enthalpy of reaction, the delta H of reaction. We don't talk about the delta H of formation here, but ultimately we look at the difference between the bonds that are broken, which require energy, and then the bonds that are formed, which give off energy. And drawing good Lewis structures is key to doing this properly. And we'll look at an example of this later or in another video. Now, this is something that I can't highlight enough for you guys, which is that drawing good Lewis diagrams is probably the most important skill that you have to develop to get through the rest of the course. Almost everything else that comes for the whole rest of the semester depends on being able to draw good Lewis diagrams. So it's worth the time to go slowly when you're drawing molecules to check, is this a valid Lewis diagram every single time you draw a Lewis diagram? Even when we start doing things in 3 dimensions, when they start getting more complicated, it's going to be critical. Now, the next topic I want to broach is one of bond polarity. So, electrons aren't always evenly shared in covalent bonds. Okay. Now, this is a kind of diagram that I want you to get used to looking at, where this is a charge density map. All right. And what this shows us is that the fluorine in HF has a high charge density around it, and the hydrogen in blue has the fluorine has extra charge around it. It's not negative, it's not fluoride ion, but it has charge around it, and the hydrogen is missing. It has blue means positive. It's missing electrons. And if you look at how this is represented, we have lowercase delta, which means partial for the charges. So the fluorine in HF is partially negative, and the hydrogen is partially positive. This bond is polar. The 2 electrons in the bond aren't shared evenly. This can be represented like this, or as what's called a dipole moment, which is a vector. Now, this polarity comes from a property of atoms known as electronegativity. And there's a trend to it, and we haven't looked at it yet. But ultimately, as we go up and across the periodic table, elements become more electronegative. And you can think of electronegativity as the ability of an atom to attract other electrons to it. So what happens is when we have a polar bond, the electrons are shared unevenly. And this has all kinds of consequences for things like solubility or melting point as we go forward. And we'll see this later on. Now, a weird side effect of this is that, in fact, we tend to think of ionic bonds and covalent bonds as different in type. But in fact, they're not. They exist on a scale, right? So that really ionic bonds and covalent bonds differ only in essentially the difference in electronegativity between the atoms in the bond. So, for example, when the difference is very low, say around 0, about 0.4, we consider that to be a covalent bond, nonpolar. Then if the difference in electronegativity between atoms is somewhere between 0.4 and 2, that's a polar covalent bond. And then if the difference in electronegativity is greater than 2, we are arriving at an ionic bond. Now, the thing is that a lot of elements that we tend to think of, or a lot of compounds rather, that we tend to think of as ionic, aren't purely ionic. They have differences in electronegativity that are less than what the cutoff is. So let's take a look at an example. Let's take the case of, say, aluminum chloride. So let's take, AlCl3. So this is a metal and a non-metal, right? Al3 plus and 3 Cl minuses. So we would expect this to be an ionic compound. But if we look at the electronegativities, now I don't expect you to know these, all right? If you need them, you'll be given them. Aluminum has an electronegativity of 1.5, and chlorine has an electronegativity of 3. Now, I don't think I mentioned this explicitly. The Pauling scale, which is the scale of electronegativity, goes from 0, although not really 0. The lowest measured electronegativity is 0.7, I think, for francium. And it goes all the way up to 4. Fluorine has the highest electronegativity. I guess 0 would be for the noble gases, right? So the delta electronegativity here is 3 minus 1.5, which is 1.5. So this bond falls into the polar covalent range of bonds. And in fact, what does this mean, right? We still can treat this as an ionic compound. It kind of behaves, in terms of how it dissolves in water as an ionic compound. Well, this is what it means. In general, ionic compounds have much higher melting points than covalent bonds because the ions are held together very tightly by the lattice energy. So compounds that have covalent character, that they show up sort of somewhere in the middle of this scale that I showed you before. I'll put it back here. Right, so these show up. So 1.5, for example, is, I don't know, let's call it about here, right? So what it means, it doesn't mean that it's actually a covalent compound. It means that the bond has some covalent character. So we would expect that compound, for example, to have a lower melting point because covalent compounds generally have lower melting points. We might expect it to be slightly less soluble in water than a purely ionic compound. So that's one of the things that you should keep an eye on when we're talking about the types of bonds.